All right, so what we're going to talk about in this video is we're going to take a look at the conservation of momentum. When we look at the momentum of an object, the most important thing when we talk about its conservation is that if a system of objects interact with each other and transfer momentum from one object to another object, the total momentum that's in that system of objects interacting is always conserved. And we define a collision as any physical contact between two objects that results in some sort of change in motion for one of them. If we want to conserve the momentum of some sort of system of collisions, we have to exclude it from any external influence. So that means nothing outside the system can be pushing on it. We can't conserve the momentum of an object or momentum of a system if something outside the system is changing its momentum as well. So we have to isolate the system. If we want to look at this mathematically, what we would be looking at is we'd say that the total momentum of the system that happened before the collision is equal to the total momentum of the system that happens after the collision. If you look at this mathematically, what we would say is that the momentum before the collision is equal to the momentum after the collision. We would expand this concept to account for individual objects that are interacting. So on the left, you can see that I have a system of two different objects that are interacting, mass 1 and mass 2, each of them with an initial velocity and each of them with the final velocity. If we determine the momentum of each of the objects before the collision, sum them up as vectors, because momentum is a vector, after the collision, we could take the momentums of each of the objects and sum them up, and the sum of all those momentums will always be the same. So the momentum is conserved for the system of objects. We combine all their initials and finals and they're equal. But you can expand this. I had this just for two objects interacting, and you can expand this to an infinite amount of objects. Obviously, that's not feasible, but there's no limit or cap on how many times you could account for this. One thing when we talk about momentum that we really need to understand, especially at the AP level that we didn't touch on in honors, was this idea of elasticity. Elastic collisions are collisions where the energy of the movement is conserved. So that means because of the interaction, there's been no loss in the energy of the moving objects, at least the energy associated with their movement itself. And we define that as an elastic collision. And we'll talk more about this in class, but I want you to just at least understand the concept of it. Inelastic collisions are what we refer to as collisions where the kinetic energy of the moving objects is not conserved. Again, we'll expand upon this in class, but elasticity means that through interactions, no energy is lost for kinetic energy. We talked earlier in the notes about the center of mass and its conservation. When you look at conservation of momentum within the light of center of mass, there's two things that are really important. The first thing is that the center of mass, or the momentum of the center of mass of the system, will always be constant. In fact, as the mass is moving, the center of mass, the fact that the interaction actually happens, the collision happens, doesn't change the velocity of the center of mass. This is extremely important because if you can look at trying to understand how the center of mass of a system is moving before a collision, you can use that movement to understand how it's going to act after the collision. And we will try more examples of this in class. Right now, we're going to try to work on the fundamentals. So let's look at a few different types of collisions you can have. There's three ones that we generally talk about. Collisions that stick together. These are generally inelastic. Actually, collisions that stick together are always inelastic. We have collisions that bounce apart. Those are generally elastic. Collisions that bounce apart can be elastic or inelastic. Generally speaking, they're elastic. That's why they bounce. And then we have collisions. Collisions are always inelastic. So the first and the third are always inelastic. The second one is sometimes elastic, sometimes inelastic. I would like to just go through an example of this, and we're going to take a look at an example of collisions that stick together. In this example, we'll have all the momentum in the before equal to all the momentum in the after scenario. So let's take a look at the situation. Your 70 kilogram friend is so happy to see you that they run at you with a speed of 5 meters per second. So you're stationary and you have a center of your mass is 70 kilograms. When your friend reaches you on impact, they pick you up and sweep you off your feet. What I want to know is what speed are you and your friend moving at after you pick someone up? I hope it might occur to you that if you run up and pick something up, something that's massive, on the act of picking it up, it'll have some inertia that's going to slow you down. And then you're right after the interaction. If you pick up something stationary, you always have a little bit of a drop in speed yourself. So let's find out what that drop in speed is. In order to do that, we got to figure out all the momentum that's occurring before and all the momentum that's occurring after. So here I've written an equation to capture this. We have mass 1 times velocity 1. We don't have two masses or two velocities here because initially object 2 is stationary. So all we have is the mass of the first object, your friend running at you, and their velocity. That entails all the momentum in the before condition. After your friend picks you up, you and your friend are now moving together as one mass. So you have to combine your mass together, and you can find out what your final velocity is. Using the numbers from our equations, or from our problem, your friend was 70 kilograms, moving at 5 meters per second. That will give you your total initial momentum. Afterwards, you and your friend are going to have a total momentum of, or a total mass of 140 kilograms, but you and your friend together must still be moving at the same momentum. So 70 times 5 divided by 140 will end up giving you a final velocity of 2.5 meters per second. In this example, you saw that the momentum before is equal to the momentum after. What I would like you to do is, after you complete this, you have 2 more examples in your notes that I put into your Nearpod. So try those. The keys to them are right after. And then once you complete all that, you'll have a CAS Learning example that's really going to focus on the fundamental Regents and honors level of momentum. And we'll get up to speed on that when we get back to class. We'll take a look at this and practice these concepts a little bit more, as well as try to expand a little bit about center of mass.